Hello everyone, this is the tutorial video to homework number 1 in ENSC 110 and LRES 510. So remember from the field week, on the first day, Monday, and a little bit on Tuesday, we went out and we collected data and we recorded plant species occurrence in a number of different frame sizes and frame shapes. And in this homework, we're going to use that data to build species accumulation curves. So the goal of the homework is to evaluate plant species richness and species accumulation in an agricultural setting at Fort Ellis and the more natural setting up in Highlight Canyon. The objectives are to analyze your nested plot data and create species accumulation curves for Fort Ellis and the highlight site, and evaluate if species richness differs in 0.5 meter squared circles and rectangles. Create a species accumulation curve for the large modified Whittaker plot, and interpret the results and begin writing them up. This interpretation and writing up will help us practice for our final projects. So all the data are on D2L under homework number 1. So the first part of the homework is the nested plots. So using the data we collected, we want to calculate the number of species recorded in each of the different sizes across the treatments organic grazed, organic tilled, and chemical, and for the different circles and squares. So the data set is called Fort Ellis data.csv, and .csv means comma separated variables, and that's a type of text file. So the first thing we're going to do is go to R and open it up. So R's opened up, and I have my GUI window present. And now I need to open the homework script that's on D2L and set my working directory. So the first thing I'm going to do is set my working directory. And on a Mac, it's the straightforward command is Apple D, and that'll bring up my window, and it says choose new working directory, and I'm going to go to the homework, and I'm going to choose homework 1 as my working directory. It depends on where you put your file as to what exactly your working directory will be. So now I'm going to open my script. But quickly, in Windows, the command is under miscellaneous change working directory. You can also type the command set wd, and it told me that I have an error, but you should be able to just do # set wd, and it will load up fine. And you can see if you want to do it that way, you can set wd, and your directory is where it will be noticed. So then you can take your path out of Windows Explorer, for example, and just paste it in with d equals the path, dir equaling the path. If you have any problems with us, call us, email us, contact us, and Kim and I will help you guys figure that out. So now my working directory is set correctly up here. I know my working directory is set right here to homework 1D. Now I'm just going to press command open, and I'm going to open the homework script right there, and it pops up. So the homework script is on D2L. Download it, download the data, and put them in the correct directories where you want to store your things. So here's an example of how Kim set her working directory on a Windows machine. So we'll start right here. The first thing I need to do is read in the data. So we're going to use this read in the data, read.csv. And the data's in the correct format. And I'm just going to press Command Enter or Control R on a Windows machine, and it will run the first command line for me. And we can see over here that I didn't get any errors and that the object FE is the Ford Ellis data now. And we can see that here just by calling it up. Command FE, oh, there goes the data. That's a lot to deal with and very difficult to deal with. So you don't often look at the raw data in R in this respect. But you can simply look at the names. So we can see the names of our data, our columns. It will give it to us here. Our site, whether it was Ford Ellis or highlight, the treatment type, the shape of the frame, the initials of the recorder, the area that the frame covered, and then the presence and the absence of each of the individual species. We can see the dimensions of those. Note here that we have Trigopogon dubius is column 19, Trifolium repens is column 20, and Triticum aestivium is number 21. So why is that important? Well, if we run this line of code, the dimensions, we'll see we have 84 rows, our observations, and 21 columns, our species, or the 21 that I just counted to here. So sometimes it's nice to see the data and see what the data sort of looks like. And you can do that simply by typing header or head, and then FE, just type head FE and call it up. So here's what our data looks like. We have site, treatment, shape, as I just went through, and then the presence and absence of the individual species. So the first question in the homework, if we bounce back over here, is calculate and plot a species accumulation curves for the different treatments and the circles and the squares. The data and so that means we need to think about summing up richness in each one of our plots, and then we need to subset them in the different categories so that we can graph them simply. So now let's go back over to our script. So the first thing here is we'll look at FE treatment. And I can switch over. Okay, there's our FE treatments. We have 3 levels denoted down here: herbicide, organic grazed, and organic tilled. And we've seen already that we have 3 levels, and now we can call it the same. We can see the levels for shape, and we can see that we have circles and we have squares. And then we can just have a quickly look. Remember the notation, FE denotes the object, and in this case, the object is a data frame. So this is how our data is stored. And then when you give it a $, it's looking for, the $, means you'll be, the next text will be referenced within that object. So the name of that object, the column name in this case. So if we call FE, we just get the data set. If we call FE $area, we'll get just this column in the data set, which indicates our size. So here we go on to the homework, on to answering the first question. So the first thing we need to do is know how many species were in each one of our plots, regardless of its size, shape, frame, anything. And that means we're going to sum the species, which start here at column number 6 and go through column number 21. So here we denoted that we want object FE, the Ford Ellis data, and when we give it a hard bracket, that means we're identifying a specific portion of the matrix. And here we didn't put the format is rows, then columns. So we didn't write anything in before the rows here. So the automatic default is we'll get every single row. But here we want only the species and not the data that indicate the size, shape of the frame. So we want to start with column number 6 and go through column number 21. And so that data, we can just run it. If you isolate and highlight data in your script, then you can run just that bit of code. So that's just going to call up, if you see on the back of 1, that'll just be our 1s and 0s for presence and absence of each of the individual frames. And because our data is already in the form of presence absence, we can simply sum across rows to get the richness of species. So we'll do that by executing this row sums command here. And you can see it popped up down low. And I only highlighted the latter portion, so I didn't save it as an object. So I need to save it as an object now. And now we have it all added up. So we know the richness of each individual plot that we recorded. So now we're going to go and we're going to subset the data apart so that we can make a graphic more simply. So the first one here is Fort Ellis organic tilled. This one is the other organic treatment. Oh, this is organic squares and organic circles. So how does the subset command work? So the subset command, highlighted right here, is a nice wrapper function. So I'm saying, within the context of subset, take FE, the Fort Ellis data, and then where the Fort Ellis data $treatment equals, which is a logical statement here, organic tilled, give me those values. So subset it just to the point where there's organic tilled. So we'll do that. We'll run the code. And then we'll just add in one quick thing here. We'll type the dimensions of this now to compare it to above. So the dimensions of FE. So now we have 28 rows that were from the organic tilled portion, and we have 22 species for the 6 through 21 there. Oh, sorry, that's incorrect when I described this. The 22 is for all 21 rows that we had in this original data set, plus we made a new column in the data set, FE $richness. And now we have 22. You'll be able to see that by typing names, FEOT, and you can see that richness is the new one that's on the end after astevium. So now we can move on. We've subsetted that bit of data, but now the homework question asks to separate the circles and the squares. So now we can take this FEOT object that we created right here and subset that object, but this time instead we are going to separate by shape, and we want to have just those instances where it equals square. So FEOT $shape equals square. And you could actually run this bit of code right here and you can see what it ends up looking like. It gives you a whole bunch of trues or false, so logical statements. And the way logical arithmetic works in R is there's always two together. So there's greater, so here we define, maybe not in this script because it's a bit older, but often we'll use FEOTS and just put an equal sign, one equal sign right here. And that means that this object created here will be equal to this name. But logical operators have two all the time. And so equals means that it's going to logically address whether FTO shape equals square. You can put less than or greater than here. You can put exclamation point, that means non-equal to, and we'll come back to that later in the data set. So Now we can do the same thing for circles and squares. We perform the two subsets. Called them up, and now we can look at just the circle data. So you can see what it looks like. Now we have just the circle data shape, organic tilled, and we have all the different areas right here. So now I'll bounce back to our script again. And now we can calculate, we'll take that data, and for the squares, we'll calculate the mean richness by area. And the reason why we're doing it with this function here, which I'll explain in a minute, is because we have multiple observations from the same size. J and E sampled 0.1, and CMC sampled 0.1, both of the circle size. So we want to be able to take the mean of that. So we're going to use this, we're going to take this vector right here, our richness, and we're going to use this tapply function. And tapply means to apply a function to the table, tapply. So we're taking the richness vector, and then we're giving the second criteria here in the middle is by what? We're saying that f and of the squares here, all the different unique areas that are associated with area give us the mean value. So now we can run that bit of code, and it works fine. And now we can call up the data, and now we have the mean sizes for 0.01, 0.1, 0.25, 0.5, 15, and 10. So it calculated the mean for us based on all the unique values within FEOTS $area. So if you want to see what that would look like here, I'll copy this, paste it here, and then I'll put unique around it. And you can see that those are our unique values. So that's what the table apply function does, and it's actually handy. And as we move on further in the homeworks, we'll show you how to add more combinations into this portion right here so that we can calculate means and standard deviations across more than one treatment. So we just have to do that now we have this object OTS, so this is the organic tilled squares, the richness. And now we'll do the same thing for organic tilled circles richness, and then we'll have that data, run it all. Now we got it. Now we just have to plot the data to make our species accumulation curves. So it's a little finagled and a little tricky, but basically remember, a plot is always X and Y. X comes first, then comes Y. So with plot here, we need to first give it the area of the sizes, and that actually got saved in a funny way in the tapply function. It became the name of the column, so we can call this names OTC rich, and you'll see those names are still there. And then you'll see that OTC rich is our Y right here, and then we're telling it a bunch of stuff in here. We want type equals the line you should plot, and we're saying both. We want both points and lines, and then our Y label should be equal to species richness, our X label should be equal to frame size, and that the main should be organic tilled, and we want to constrain these values right here with the Y limit, and we have to give it 2 because we want to tell it its limit, its lower and its upper limit. So that's why we're using the C concatenate function again. So we're telling the Y limit between 0 and 8, so the graphic window will plot nicely. None of this beyond the X and Y is necessary, and R will default just to the default settings. But we like to be able to manipulate our graphics. So now let's plot that. There we go. That's what our organic tilled squares look like, if I'm not mistaken. Nope, those are the circles, OTC, sorry. The organic tilled circles, and you can see our different frame size and our species accumulation curves. So at 10 meters squared, we sampled about 7 species. And then, since we added in our circles, now we need to add in our squares. And we don't need to call up plot again. Now we just need to specify the points. As long as we haven't closed that window and we have an open graphics device, we can just give it graphics commands now. So now we'll use points, and we'll do the same. We'll add that, and we'll put squares where squares should be, and circles where circles should be. And so we did that here by making squares, by making PCH, that's the point character, and the color 2 was the color red. And you can look all this stuff up on the internet. It's all over the place on the internet, and there's lots of cookbooks out there and lots of ways to do this. But then so back to the homework question. Now we want to also add in a legend so everyone can see it. So we added in our circle squared legend for organic till. So really, all we have to do now is repeat that for each and every one of these groups for question 1. So we have our organic tilled, circles and squares. We need to do this for the organic grazed and the conventional. So that both can be done really easily. Right here is the code. And we calculate the exact same thing, just changing the names here to organic grazed squares and organic circles. We just change those names so we don't write over the objects that we have. And then we can just plot those all the way up. I'll just run all that code at once. And there's the circle and the square data for the organic grazed treatment. Pretty straightforward. This makes R a powerful tool because we really only had to just copy this code right here and change a few things and we can redo it. That's the beauty in having a script. And we'll do that for the herbicide treatment as well. Here we go. And we got the herbicide treatment exactly the same. We moved the legend in place a little bit so that it's not in the way, but basically the legend works here by 7.5 by 2, that's telling us, right, we want it at 7.5 on the X and 2 on the Y. That's where it starts plotting it at. And then we have the same thing. So there's a little bit of how you could evaluate question number 1. We could also calculate the standard deviations between these. And so you can see we're using the tapply function here, just like we were doing above. But instead of mean here, we gave it SD for standard deviation, and we could calculate those out. And we'll save them, and now we can just call up the object itself. I'm just highlighting it and sending it over. You can see there's what the standard deviations are, quite small for organic squares and circles. A little bit more variation, a lot more variation between the outer ones. So that's the way to think of question 1. I think the code's all there, and I'll leave it up to everyone else. I'll leave it up to everyone to interpret it and print it out. So now we'll move on to question 2, and this is going to use data from highlight circle squares data 2015. So we also had rectangles, but it made the file name too long. So question 2 asks, calculate the mean number of species and the standard deviation for each plot size and frame shape using the highlight nested data. So first we need to separate the circles and the squares like we did last time. First we're going to read in the data actually. From highlight circle square data 2015, I highlighted it, read it in. I can look at the names again. You can see we had many more species in this one. Let's see, the first species starts at 6 again. So we had 92 minus 6. We had 86 species that we recorded in the Whitaker frame, which is quite a lot. So I'm going to close out the graphics and move back to the script here. So now we need to calculate the richness. And again, because we're setting up our data in a standardized way, the way that's expected by many packages in vegan is that the rows are observations and the columns are species. So again, to calculate the richness, we just need to sum across the columns. So here we're using this row sums command, and this time we're taking HD for highlight data, and we're using the hard brackets to indicate where in the matrix we want to sum, what and we're saying we want all rows because we didn't put anything in before, and we want to sum columns 6 through 92. So send it over. HD $richness is now our data here. So now we have the richness for the highlight, circles, and squares data. So we just have to go through the same process essentially that we did for question 1. We'll subset the highlight data based on circles and squares. Highlighted it here and send it over. And then we've subset that data. We see that it's there. And remember that now we have our richness as the final column in the data set. So there's $richness. And so we just need to do the same for the square data. And we're subsetting just like we did last time. We're saying subset highlight data by the highlight data shape where it equals the square and the logical indicator. So Command Enter, we have all that. And now we're doing the exact same thing that we did in the first homework problem. We're finding the mean based on all the unique values of area for the circles and the squares. So we did that. Now we can see that here. And we can see that here. So we have both of those already. If you didn't want to set them out into different objects, we can do that like this. We'll take SR richness and we'll put it in there. We want to do the same, but this time we're going to give it a list and we're going to give it S dot. We are going to give it, actually we're going to have to back to the HD data, sorry. We're back up to the HD data, the highlight data, because we don't want anything subset here. And we're going to do HD $area and HD $shape. And we want to get the mean. And then we'll send that over. And you can see that we got the same data here, the circle with the different sizes, and the squares. And if you guys will recall, we only did circles and squares except for 0.5 meters where we did all 3 of them. So that's an important answer right there. You might want to come back to it. And I'll leave this in there and save that into the homework script. So now it's going to be your turn to write some code. And I won't give away the answers right here. But basically you need to take this tapply code that's up here and substitute mean for standard deviation to get the standard deviations that belong in there. Alternatively, you could do this right here and substitute mean here and add standard deviation. So, but with that data that we just worked on, we need to take this information and make the species accumulate, or we can compare the species accumulation curve for highlight and Fort Ellis. So you remember we had the data from Fort Ellis and we had the data from highlight. And so here's the highlight data with the CM and SM for, I don't know why we gave it an M. We just named it an M. I guess for circle mean, square mean, this is for highlight. We can make the same thing. So think about that. There's the species accumulation curves for the circles and squares and highlight and how many species each one of them has. You could definitely compare that to the circles and squares from Fort Ellis. I'd be interested to hear from you guys what you guys think the differences are. Okay, there's one other way that we could possibly do this. And first we're going to get rid of our rectangle data in this one. Because remember, when we ran this line of code right here, we saw that we only had 0.5 meters squared. So this is an example of using subset, but instead of equals here, we have exclamation point equals, and that means not equal to. So that would be an equal sign with the bar slash through it. But we can use that to subset. So now we're saying subset the highlight data based on shape, and we want everything that's not equal to rectangle. So we're going to call that no rec, and we ran it over there. We got no error messages. Looks good. And so now we can make the box plot. We can make a box plot like we did when we talked Wednesday afternoon in class. We talked about making box plots. And here we're using this different notation, richness as a function of area. But for this one, we don't need to add the $ and then no rect before richness and area, because we specified here in the data that the data is equal to no rect. So now we can just give it column names. Run that one. You can see that it comes up right there. And now you can see what the different size shapes and the different species accumulation curves are with variation. So think about those last couple, especially of the squares. Definitely some variation in there. So now we did the mean and area before, but now we've answered the questions about species accumulation and the different means and the different standard deviations of our plot size. And now question 3 is, does species richness differ between the rectangles, the circles, and the squares? So we already know those values from up here, right? We can slide back up here and we can figure that out with just this little line of code. We can go over and look at it. Very interesting. Does the difference in perimeter make a difference? I guess that's what question 3 is about, right? We had the quiz question a while ago and we talked in class. Does having a larger perimeter capture more diversity? You guys will have to answer the question to number 3. So I showed you how to do it with this line of code right here. But then another way of doing it is by doing the simple subset and the t applied just for the rectangles only. And then we got 0.5. You can see this point 10.4 matches this 10.4. So then you should do that with the standard deviations as well. Get the answer. Yeah. So now if we move on and we've seen the plot and we know the answer, 9.3, 10.4, 9.25. But do those values differ from each other? So here we're going to subset out just the data that has the highlight data where the area is equal to 0.5. So let's see what that looks like. We probably got to run it first. And then we can call it up and see what it looks like. And there we get this big data frame again. So we might want to know the row sums of just this. So I'll just quickly calculate the row sums. Oh, we have to be numeric. Oh, because we have the wrong ones in there. We need to have just 6 through 21. Oh, but that's not the right one anymore in this one. So maybe, yeah, we'll see. Let's see. How we had 90 some species. Let's go back and call up the dimensions. That will help us actually. So we'll add in the dimensions. We have 93 species. And we added that richness on, so we know we really only want 92. So we'll call up 92, and we can see there's all our values for just areas of 0.5 meters squared. It doesn't indicate whether they're circles or squares, but we're not so much interested in that quite yet. We just want to check the data to make sure it's correct. So now let's box plot the data and see what everyone's variation looked like. So now we're using the box plot command like we did the other day. And now we're writing it in we're writing it in the formula notation, the other notation. So now we're saying that circles, squares, rectangles in 0.5 meters, the richness as a function of the shape. So, and then call that up, run that line of code, call up the graphics window. And you can see here are the values. And you'll remember, think of the values that we had when we just calculated the mean, right? 9, 10.4, 10 something or other. So do you think any of these statistically differ from each other? I hope you guys are thinking of the right answer right now when you look at it, but we can then formally test it by making this linear model here, just like we did on Wednesday afternoon. So here we're telling it the data is equal to S.C.5, and that we want to have richness. We want to model richness as a function of the shape. So we'll run that, and we'll call our object here mod for model, and we can call up the summary statistics. We can see that here are the summary statistics with some different p-values in there. And you can see that our adjusted R-square is really, really low. So our adjusted R-squared would be how much variation we're explaining right here. So how much variation are we explaining? We're explaining so little variation that we've gone into the negative numbers. And these p-values, this is for the slope of the line, and you can generally ignore this. And this would be the circle, yep. So remember 9.33. And if you add to 9.33 1.00067, you'll get the 10.4 for the rectangle. And if you take 9.33 and subtract this number, you'll get the number for the squares. Compare those to the t-values we got. That's how you back calculate the coefficient estimates. And so our p-value for this model is 0.73, so 70.73. Does that seem significant to you? You'll have to answer the question. So now we'll move on to keep it moving here so this doesn't get too long. But we'll move on, and now we'll calculate the species accumulation curves. Question number 4 for the Whittaker data. Remember, we set up this nested Whittaker data plot. And first thing, the first part of the question is oh, wait a minute. Okay, so the first part of the question is calculate the cumulative species richness for each plot size. So we're filling in this graphics table number 4 right here. And so the NAs under standard deviation for 5 by 20 and 20 by 50 are because we didn't have more than 3 replications of those. In fact, there was only 1 each. So those we can't calculate a standard deviation on. But here we go on the calculation on the first part. So first, for the Whittaker data, we need to read it in, and we are going to name the object modified Whittaker because MW for modified Whittaker. I don't really want to look at the data frame. I'll just call up the names. You can see there are all our species, 87 species we had in the data set, or 87 total columns minus the recorders, the frame size, the area, and the plot, which is our identifiers. And then the richness and the total cover are right there. Chris was nice to add it up for you. So first we're going to subset the modified Whittaker to modified Whittaker where the area is equal to 1. So that would be our 0.5 by 2 meter frames, the small little subplots around the edge. And we can just calculate quickly the mean and the standard deviation. All pretty straightforward. You can just add those right into your homework. And now the 10 meter plots. So these were the larger 10 meter plots that were 2 by 5 meters. And there was a couple of these, so we can calculate those quickly by doing the same mean and standard deviation. Oh, we called up the MW there at the end, sorry. So the mean was 15 and the standard deviation was 0. So there was no variation because we only had 1 set of recorders. And I think only 2 plots. They must have been exactly the same. So then the species accumulation. So now we need to take just the small plots and just the species, the vegetative species, and we can call that up again. If we need to see that, we can call up head MW. Oh, let's do small because we want to see what we're using there. You can see here's our data frame. So we can slide up. And here's column 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we want to start right here with 10, Abies lasiocarpa. So this is not the actual answer to the question, but this is something that we can use. So we can use this libraries and packages in R. And this one we're requiring vegan. We're saying require vegan. And it'll say it's loading the necessary packages, vegan and permutate. Now this package is already on my computer, but if I didn't have it on my computer, I could go to packages and package installer and click on it. Now it looks a little different on a Windows machine compared to a Apple, but I can just type in here. Well, first I can say get list, and you can see how large the list is. This may take a second because there's a lot of packages out there. You can see here is the huge number of packages. I don't know how many they are, but we just want package vegan. And here's package vegan right here. And I click install dependencies and install selected. Now this will it'll take a minute to download, but it's executing the command. It's doing it, it's downloaded, all this stuff. We have the binary packages. And now I can go back over here and type library vegan and press enter. Or I can do it like in the script and say this will require vegan. Doesn't matter. Either way, they're essentially the same. So now we can make a species accumulation curve using this function from the vegan package called spec_accum. So we'll just run that like this. We'll run it first, and you can see, okay, it did it. What are all the, so for 1, 2, 3, 4, 5, 6, 7, 8, and you can see what the site richness. But really what's nice about this is that it can be plotted. So you can see our species accumulation curve. What do you guys think? This is just for the smallest plots, and this is not the answer to your homework. But you can see, maybe we're starting to get to an asymptote, maybe not. And then you can plot the variation associated with that by making a box plot. And see where the outliers are and what the variation is like between the two. But I repeat, that is not the answer to question number 5. So question 4, you need to fill in the table. And now question 5 right here, you need to make the species accumulation curve. So we need to calculate, we can take these numbers, and we're using this concatenate function again. So we remember we can take these numbers for the ones that don't have any replicates, and that's just a little bit higher. So so we had 15 species in the 2x5, 32 species in the 5x20, and 54 species in the 20x5. And all that can be found right here where we read in the modified Whittaker plot. And we sum across the rows. But actually, we didn't even make you guys sum this year. You can just look at the richness vector within the data. And so, but we need to calculate the mean species richness of all these small plots. So we'll borrow this object that we already calculated up here. And that was the vegetation for right here. We could sum across rows, but Chris was nice enough and made you guys the richness vector. So now we just need to, and that looks like this for each one of the rows. And now we just need to do the mean of that. which would be 12.75. And then we have the other numbers in there, and then we're going to concatenate those into one long value, and that will be our new, what we're calling richness here. And we'll just run that, and then we'll call up richness. You'll see it comes out looking the same. And then we're going to just concatenate the areas of our plots, because we know they were 1, 10, 100, and 1,000, and 1,000 in a nice logarithmic form, adding an order of magnitude in each time. And then we're going to plot the answers. Oh, sorry, I didn't save area. Now we'll plot the answers. And there you go. We can just switch over and look, and we can see. So these graphics, and then the rest of the homework assignment, we want you guys to save the graphics and put them into a small report form, which is listed at the bottom. And if you have any questions on what we want in the report, post it on D2L or contact Kim and I, ask her in class on Friday, or post question on D2L for the 510 online section. And you can have a look. But to save the graphics, on a Mac, I usually just press Command S, and it will save automatically. It'll give it this name rplot.pdf, and I can save it wherever I want on my computer. I can call it Bob or something. I can call it whatever I want, and the automatic format from the Macintosh system is in the Unix is a PDF, which is actually really nice. You can manipulate it in Photoshop, you can manipulate it in Illustrator or Adobe Acrobat or anything like that if you have to make small changes to it. So with that, that ends the first video for the homework. If you have any questions, D2L or email us directly. Good luck with the homework. See you all soon.